1, 1, 0 for these traces, or it's 1, 1, 0, 1. It's in one of the hypotheses. Then we can actually just calculate the differential trace for each of these, and I'll show you what the effect is. Because basically, we presume that one of the hypotheses is right. Now we don't know which one beforehand, so we're going to try them all. So either a hypothesis is right or it's wrong. So let's first see what happens if you take a wrong hypothesis. Again, we're going to calculate this differential trace. So the first step is we're going to group the data differently. So here we've grouped them by the wrong data in both cases. Now if we calculate the average here, these will statistically actually not differ at all, because you've done something wrong and it just all gets messed up in the grouping. So what you see is noise. Now if we group according to the right hypothesis, we get back into the original situation where there is a statistical significant difference, and when we subtract, we actually get these peaks. Okay, so that's all kind of tricky and to get your head around, and it's going to get even more complicated in the next few slides. But the bottom line is, if our hypothesis is incorrect, we get nothing. And if it's correct, we see these peaks. Up to now, I've been talking about this input bit. But the cool thing is, there's no restriction on that. I can also start predicting stuff that's going to happen inside the algorithm. So this tool actually allows you to, if you have a restricted set of hypotheses on what the data is being processed inside the algorithm, you can also run this trick. Now that's kind of cool. So now we're going to look in what the effect of this is on crypto. So here I plotted the DES algorithm, which is still the most widely used algorithm in smart cards nowadays. Actually triple DES, but it's made up out of 3 DESs, so we're just going to break 1 DES. So as you may know, you send in plain text, it does some kind of permutation, and it goes through this Feistel scheme, and then the answer comes out. Now that's great. And in every round, it mixes a round subkey. Now we're interested in these guys, because in the case of DES, if you have 2 round subkeys, they will actually make up the full key that you're looking for. Now if I zoom into this Feistel function, what you see is that the data is going in, it's being split in 2 halves, and half of the data ends up in this E permutation and gets XORed with the subkey. So we actually know the data going into this algorithm all the way up to here. Then it gets XORed with subkey, and then we're lost. It's 48 bits. We don't know what they are. But the next step is that they're being spread out over all these S boxes. So the S box output here, so 1 bit of S box output depends on 6 bits here, which actually depends on 6 bits we know, and 6 bits of subkey. Now that's the kind of thing that we're looking for when we're doing, in this case, differential power analysis. We're going to chop up the key into little bits, in this case just 6 bits, and we're going to try to break them one by one. So let's again assume we have 1,000, 1,000,000, a bunch of traces. For each of these traces, we know the data that we sent in there. So for each trace, we can calculate the data all the way up to this E permutation, up to this XOR with the subkey. After that, again, we're lost. I said that. I said this as well. We know this part. We don't know the subkey. So that's our question. How are we going to figure out these 6 bits? Well, we're going to run what's called differential power analysis on it. We're just going to try, I mean it's 6 bits, 64 possibilities. We're just going to presume each subkey in turn. And then we're going to calculate these differential traces based on each subkey. So in the first case, we know the data going up here. We presume the subkey is 0. And we input this into the S box, and we're going to try to predict this output bit. So this is again the hypothesis testing I've been talking about before. So we take n traces, and each of these 6-bit subkeys leads to a different hypothesis for the S box output. So we're going to end up with 64 hypotheses, of which one must be right. One of the subkeys must be the right subkey. And we're just going to calculate a differential trace for each of these 64 possibilities. Now, what you get is this nicely twisted number of traces. I'll flip them around for you, but this is just to display to you that we have n traces, but we always end up with 64 differential traces. What we see is that there's actually one key candidate where we see these peaks. Now, what does this mean? If we see peaks, that means that we've done the grouping correct in the differential trace. And if we've done the grouping correct in the differential trace, that means that the real data actually must match our hypothesis, which means that we know the subkey for this. Now, if we just keep on doing this for all the S boxes in the first round, and then we do it all for all the S boxes in the second round, we can actually deduce the full key. So using this method, we can go from knowing nothing, just measuring the power, doing these differential traces, and retrieving the key from an implementation. And this works just as well for AES or for more like asymmetric crypto algorithms like RSA. There's different techniques. But this is really cool, and it's mind-blowing the first time I saw it. So, well, once you've done that, I guess you can go home and have a beer and enjoy your victory. Just a small reality check. Of course, smart card manufacturers know about DPA. So they implement all kinds of countermeasures. And for us, it's often difficult finding the correct kind of filtering and alignment things. But it's still, in the end, it boils down to doing the same type of analysis. Your pre-processing may be a little bit more complicated. Countermeasures, we find them in both hardware and in software. So in hardware, we see like noise generators on the power line. We see random pipeline stalls to create misalignment in the processes. There's all kind of things going around. On embedded systems, we don't see them that much. So that's more of an easy target in a way. To go into fault injection, that was sort of the side channel analysis part. This is the side channel attacks, or the fault injection. We're going to try to cause a temporary fault in the program. So we're not going to burn our chip, hopefully. We just want to switch one transistor at some point in time and see what it does. This has actually been traditionally studied in the failure analysis. For instance, in space technology, they have a problem there with X-rays and all kinds of radiation bombarding chips and causing all kinds of failures. So that's where it comes from. And there's different channels that you can glitch. You can glitch the supply voltage of a chip. You can glitch the external clock, which is on smart cards, the clock is provided externally. And you can go into the cool kind of laser glitching stuff. Now, the effects of fault injection can vary. But basically, your targets are branches, like if pin is correct, then do this, else fail. Well, that's a nice one to glitch. All kinds of state variables, for instance, cards that are able to lock themselves, you could unlock them. Crypto is a whole different ballgame. You can actually insert errors in your crypto algorithm, and by comparing them to regular executions, you can derive the key, which is differential fault analysis. Skipping instructions you could do. Sometimes you can null crypto bytes, thereby reducing the entropy of the key. I mentioned differential fault analysis. Bell core attacks are pretty cool.